Okay, physics. Happy Friday. We are looking at a lesson on the 21st. And we had just talked about yesterday, Mr. Young, Thomas Young, had come forth with his experiment and showed through diffraction of light through two slits that light is a wave. And we were wondering what it oscillates. Let's pick it up there. What medium does light oscillate? All right, so it's going to move something up and down. And we know that when we threw a rock into the water moved. When we did our slinky, the metal in the metal coiling moved. But what is it that oscillates up and down when, I know, we can do another one we do know, is let's do the wave. So starting with Maggie, go around. You guys in the back can work together as one, and then finish with who sits over there in physics. I guess it's Andrew. So let's do the wave. So Maggie, start. Arms, two hands up. All right, go on across the room. All right, that's pretty pathetic. All right, imagine a big stadium. What is the medium that creates the wave? It is arms. So what does light move, especially when we're thinking about the sun and the light coming from the sun to planet Earth? All right, planet Earth, and here comes the light, and we are wondering what it oscillates. It was Mr. James Maxwell that I erroneously mentioned the other day. Now I can mention him correctly, except I haven't spelled it right. Maxwell, James Maxwell. And he was the first one to theorize, and we now accept it as true, is the thing that oscillates, the medium through which a wave propagates, the light wave propagates, is the electromagnetic spectrum or field. Let's call it the electromagnetic field. All right, so before we go any further, let's take our day 5 notes, day 5B, light as a particle. So we're going to look at light in a different way today, and we're going to take some notes alongside, starting with what Mr. Maxwell had to say. So take your day 5B notes, and they'll be given out by your substitute. Many thanks to whoever ends up substituting. I don't know who that is right yet, on Friday, 4th period. So many thanks to whom it may concern. All right, so on those notes, please indicate that James Maxwell identified what medium does light oscillate, and it was the electromagnetic field. So on those notes, I drew a picture of the electromagnetic field, and it looks something like this, in that the electric field might go this way. So if I'm going back like that, and perpendicular to that is this is the electric field, and this is the magnetic field. It goes at right angles to it. So you don't have to draw it. I took a picture of it there. But these are at right angles to one another. So this is the generally accepted view of a light wave, where we have magnetic, and say the thing is traveling that way. The magnetic field and the electric field oscillate at right angles to one another. So it's doubly cool. All right, so we have that accepted idea that there really is a substance that light is oscillating. Let's look also at, just like sound waves, if you recall when we were talking about sound waves, you don't have to write this because you already have it, but just reviewing, sound waves they have amplitude and they have frequency. So what does each of those dictate? So amplitude determines what about sound, and frequency determines what about sound. So it turns out, if you remember clearly, amplitude was volume and frequency was pitch. All right, we dealt with that a lot when we were dealing with the Doppler effect. All right, so let's go on and talk about similar things with light waves. So when we talk about light waves, now this is something you can write down. Any spot you can find along on that, it won't take much room. But light waves also have characteristics that are dictated by frequency, and amplitude. And it turns out that the frequency of a light wave determines its color or wave type. So let's look at our sheet here. And you can see here all the different types of waves, and here's their frequencies down here in hertz. So we have 10 to the 20, and we go, that's a very high frequency. Then we go down to 10 to the 6th. So that's a lower relative frequency. So we're going through gamma rays, X-rays, ultraviolet light, visible light, infrared light, microwaves, radar, TV, radio, FM radio, and AM radio. So you can see the little chart there, and here where we talk about frequency. This part right in here, which is the visible light, we can't see, our eyes can't pick up these various ones. The only one we can pick up is right here in what's called the visible spectrum. So I took that and spread it out down here so you can see in more detail some objects about, some ideas about visible light. So here on this section, I did not list the frequency, I listed the wavelength. So wavelength and frequency are very much related. So because as the shorter the higher the frequency, the shorter the wavelength, and the longer the wavelength, the lower the frequency. So we've talked about those ideas before. So I didn't actually talk about frequency here, but wavelength, which is very much related to it. So you can see the various colors have wavelengths. What is this new unit that has appeared here? Under frequency, we had an old friend, Hertz. You can see Hertz here. But now, down here, we have NM. That stands for, we actually had that probably the first day we had physics together, and it was one of the members on our ladder of units, and it stands for nanometers. So a nanometer is 1 times 10 to the minus 9. So 1 nanometer equals 1 times 10 to the minus 9. So that is a very small number. That's meters. 1 times 10 to the minus 9 meters. So therefore, if I was ever using this type of unit, I would have to switch it to meters in order to combine it with hertz and so forth. So we'll see an example like that in a minute. Before we do though, let's look at before we leave this here, I just want to mention that these wavelengths get amazingly, like here, 10 to the minus 12 meters. The wavelength is quite small, but when we get up to, say, microwaves, 10 to the minus 2, which is 0.1, so that's 0.1 of a meter. That's not that long. That's actually conceivable, a tenth of a meter. And look at the TV waves. They're 1 meter long. That's their wavelength from crest to crest. And some of these are even longer. Look at that. Down between FM and AM radio, they're falling in 100 meters long for the wavelength. Now, I thought that was of interest. All right. So, back to the drawing board here. So, as I was mentioning, so if we were going to use this formula, which also, because light is a wave, this formula relating frequency, velocity, and wavelength works not only for sound but also for light. The only thing is, the velocity of light we're going to consider to be the same all the time. We're going to use 3.0 times 10 to the 8th meters per second. So that won't be given in the problem. So they might say, here's some blue light, here's some red light. It doesn't matter. The speed of the light is going to be the same. We're going to count that as 3.0 times 10 to the 8th. Now, if the wavelength is given in nanometers, we're going to have to switch it to meters in order to combine it with and to get hertz. So frequency again is in hertz. All right, so let's look at an idea or an example. Suppose we want to use this formula and we have 1120 hertz. Let's not even use hertz. Let's mess with that unit as well. We're going to say they're kilohertz. K, little k, big H, kilohertz. Find, so we have some light. Its frequency is 1120 kilohertz. Find its wavelength. All right, so let's just step through this together. So we're going to use this formula. The frequency is given, but I want to work with it in hertz. So I'm going to take 1120 kilohertz and multiply it by, I know that 1,000 hertz is 1 kilohertz. And I know kilometer is 1,000 meters, so kilohertz is 1,000 hertz. So I cross out kilohertz and I get 1120 times 1,000. So I just move the decimal 3. So I move it over 3 and I end up with 1,120,000 hertz, regular hertz. So I'm going to go over here and put the large number, 1,120,000 for my frequency. Velocity, since I've told you that we're working with a form of light, is 3.0 times 10 to the 8th. And now I'm ready to solve for lambda. So that's our wavelength. I'll end up multiplying this over here and multiply, it disappears from here. When I multiply both sides by it, it appears here, and I divide this number by that number, and I get lambda equals 267 meters. It looks like I can only use 2 sig figs there, so 270 meters. All right, so that is how we sometimes have to mess with the unit, especially when we're dealing with light, in order to get the correct answer. All right. Today we're going to continue on our